The Andromeda galaxy hangs in the void, a serene whirlpool of starlight. But what if this beautiful spiral is hiding a monstrous secret? We are about to uncover a story of cosmic cannibalism, where galaxies devour each other in a slow-motion feast. By the end, you will understand the chilling evidence of a dark stream of victims swirling around our galactic neighbor. How can we see the ghostly remains of a meal consumed billions of years ago? And what does this tell us about the true nature of our universe? The most beautiful objects in space often have the darkest histories. This serene cosmic dance is actually a story of predation on the grandest scale imaginable. Galactic cannibalism is the universe's ultimate food chain, a process where larger, more massive galaxies use their immense gravity to consume smaller, weaker neighbors. It is a fundamental force of nature, as real and relentless as gravity itself, and it is how galaxies like Andromeda grow into the giants we see today. Picture the gravitational pull of a giant galaxy not as a gentle tug, but as an invisible, all-encompassing force. When a smaller galaxy drifts too close, this force seizes it. The side of the small galaxy facing the giant feels a stronger pull than its far side. This difference in force, called tidal disruption, begins to stretch the victim. It is a slow, inexorable violence. Over hundreds of millions of years, the smaller galaxy is not simply swallowed whole, but torn apart. Its stars, its gas clouds, and even the mysterious dark matter holding it together are pulled into long, looping rivers that stream around the predator. A helpful analogy is pulling apart a clump of cotton candy. At first, it is a distinct puff, but as you gently pull, it stretches into wispy strands that slowly dissolve into the air. Galactic cannibalism works the same way, but on a timescale so vast our minds can barely grasp it, and with materials 1,000,000 times more substantial than sugar. This is not science fiction, it is astrophysical fact. The majestic spirals and glowing ellipticals we admire in telescope images are not static portraits. They are snapshots of creatures in the middle of a lifelong feast, their current shapes and sizes directly shaped by the ancient meals they have consumed. And so our gaze settles on the predator itself, the great spiral of Andromeda. Known to astronomers as Messier 31, it is our closest galactic neighbor, a titan of starlight 2.5 million light-years away. For centuries, it was simply a beautiful smudge in the night sky, a mystery we slowly unraveled. We now know it is on a direct collision course with our own Milky Way, a slow-motion cosmic car crash set to happen billions of years from now. But that future merger is just the latest chapter in a long and violent biography. Andromeda is not merely a neighbor, it is the undisputed heavyweight champion of our local group, a collection of over 50 galaxies bound by gravity. It is larger and more massive than the Milky Way, a swirling disk containing perhaps 1 trillion stars. This immense size and gravity make it the central bully in our galactic neighborhood, a force that has shaped the entire region through its appetite. For decades, the serene image of its spiral arms suggested a quiet, orderly existence. But modern astronomy has peeled back that peaceful facade to reveal the truth. Andromeda's majestic form is not a birthright, it is a trophy built from conquest. Its vast halo, the faint sphere of stars and dark matter that surrounds it, is not pristine. It is a cosmic graveyard, littered with the mangled remains of galaxies it has consumed. The evidence of these ancient feasts is etched into the sky around it, a ghostly record waiting to be read. Astronomers, using some of the world's most powerful telescopes, have begun to trace the faint, looping streams of stars that coil around Andromeda like the ribbons of a maypole. These are the stellar intestines, the digested remains of its meals, and they point to a history far more savage than its beautiful portrait implies. The first hints of this cosmic crime scene emerged not as a dramatic splash, but as a faint, puzzling smear of light. For years, astronomers mapping the vast halo around Andromeda noticed something strange. Scattered across the darkness beyond the bright spiral disk were wispy, elongated clouds of stars. They did not form neat globular clusters or symmetrical shapes. Instead, they looked like celestial brushstrokes, faint rivers of starlight arcing through the void. These structures made no sense if Andromeda had lived a quiet, solitary life. An undisturbed galaxy's outer halo should be a roughly smooth, faint glow. These streams were a glaring anomaly, a sign of profound disturbance. Think of a calm, clear pond. If you drop a single pebble, the ripples are symmetrical and orderly. But if you thrash around in the water, the surface becomes a chaotic mess of intersecting waves and currents. Those stellar streams around Andromeda are the cosmic equivalent of that thrashing. They are the gravitational ripples frozen in time from a violent encounter. Each stream is a trail of celestial breadcrumbs, marking the path of a smaller galaxy that ventured too close and was pulled apart. The stars within a stream are all moving together on similar orbits, like cars on a galactic highway, a ghostly convoy tracing the orbit of their devoured parent galaxy. Identifying these streams required a monumental effort. Astronomers used telescopes like the Subaru telescope in Hawaii and data from immense sky surveys, painstakingly separating the faint stream light from the background glow of the universe. They were looking for subtle overdensities, slight concentrations of stars that should not be there. It was detective work on a galactic scale. The discovery of the first major stream, a vast structure now called the Giant Stellar Stream, was the smoking gun. Here was a colossal arc of stars wrapping partway around Andromeda, containing the remains of a dwarf galaxy perhaps as massive as several billion suns. This was not a minor event, it was evidence of a full-scale galactic demolition. These streams are more than just evidence, they are the digested remains themselves. When a dwarf galaxy is torn apart, its stars are not destroyed. They are stripped away and incorporated into the halo of the giant, but they do not instantly mix. They retain the memory of their original motion, flowing along like a school of fish caught in a vast current. By studying the speed, composition, and path of these stellar streams, astronomers can perform a kind of cosmic autopsy. They can estimate when the merger happened, how massive the victim was, and from what direction it approached. Each stream tells a story, a chapter in Andromeda's dark history of consumption. The serene spiral we see is merely the bright center of a far larger and far more chaotic scene of an ancient crime. But the story grew even stranger with a game-changing discovery. While the stellar streams were shocking, they represented only the visible aftermath, the bones of the consumed galaxy. Then astronomers found something far more elusive, a ghost within the ghost. They uncovered evidence of a stream not made of stars but of dark matter itself. This was the revolutionary clue, the dark stream. We cannot see dark matter directly as it does not emit, absorb, or reflect any light. Its presence is only betrayed by its immense gravitational pull. Think of it like the wind. You cannot see the air moving, but you can watch it bend trees and push clouds across the sky. Dark matter's gravity acts on the things we can see. In the case of this dark stream, researchers were studying the motions of the visible stars in one of Andromeda's tidal streams. They expected the stars to move in a certain way based on the gravity of Andromeda's visible mass, but the stars were behaving oddly, as if an additional, invisible source of gravity was shepherding them along. The only explanation was a dense river of dark matter flowing alongside the stellar stream, a separate but intertwined remnant of the devoured galaxy. This finding transformed the narrative entirely. It meant Andromeda did not just consume any small galaxy. It feasted upon a victim that was anomalously rich, absolutely packed with dark matter. Most small dwarf galaxies have a high ratio of dark matter to normal matter, but this one was an extreme case, a dark matter powerhouse. This changes our understanding of both the victim and the feeding process. The consumption was not just a transfer of stars, it was a transfer of the universe's most mysterious substance. The predator did not just grow in starlight, it grew its hidden gravitational skeleton. This dark stream is a fossil of pure gravity, a silent river flowing from a meal that fundamentally altered Andromeda's hidden architecture. What could create a galaxy so dense with dark matter, and what happens when a giant ingests such a strange and potent cosmic meal? Detecting a river of invisible matter requires a special kind of cosmic detective work. Astronomers cannot see the dark stream itself, so they must observe its effects on the things they can see. The key lies in the motions of the visible stars within that stellar stream, the ones we discussed earlier. By using powerful spectrographs on telescopes, scientists can measure the precise velocity of each star, how fast it is moving toward us or away from us. They then map out how these speeds change as you look at different points along the stream's arc. This data creates a fingerprint of the stream's motion. If the stars were moving solely under the influence of Andromeda's known mass, their velocities would follow a predictable pattern. But when researchers took these measurements, the pattern was off. The stars were moving as if being tugged by an additional, unseen source of gravity flowing right along with them. It is like watching autumn leaves caught in a stream. You cannot see the water itself, but by observing how the leaves swirl, cluster, and speed up, you can map the hidden current's strength and direction. The stars are those leaves, and their unusual motion charts the course of the invisible dark matter river. To make sense of this, astronomers turn to advanced computer simulations. They create virtual universes inside supercomputers where they can smash digital galaxies together under different conditions. They can adjust the size of the victim galaxy, its angle of approach, and critically, how much dark matter it contains. They run these simulations over and over, watching how the tidal streams form. The goal is to find a simulated collision that produces a stellar stream matching the exact shape, star velocities, and gravitational anomaly of the one observed around Andromeda. It is a process of cosmic matchmaking. The simulations that fit the data best point to a very specific scenario, a victim galaxy that was extraordinarily dense with dark matter from the very beginning. This was not a normal dwarf galaxy that simply lost its stars. It was a dark matter core that happened to have a few stars sprinkled throughout it. The predator consumed something fundamentally different from a typical meal, ingesting a concentrated knot of the universe's most mysterious substance. This dark stream is therefore more than a remnant. It is a preserved sample of a lost galaxy's true essence, flowing silently through the halo of its conqueror. The victim of this cosmic feast was no ordinary galaxy. Based on the strange signature of that dark stream, the devoured entity was something far more elusive, a phantom of the cosmos known as a dark galaxy. Picture a vast, swirling cloud of dark matter, a gravitational skeleton without a bright body of stars. Within this immense, invisible sphere, only a sparse sprinkling of stars managed to form, perhaps just a few million compared to Andromeda's trillion. This was a ghost ship adrift in the intergalactic void, almost entirely made of the universe's unseen scaffolding. Its visible light was so faint it would have been nearly impossible to spot from Earth, a mere whisper against the blackness. Yet its gravitational presence was immense, a heavyweight cloaked in shadow. This explains the peculiar power of the dark stream. When Andromeda tore this object apart, it was not primarily consuming starlight, it was ingesting a concentrated knot of pure gravitational influence. The few visible stars were just incidental travelers caught in the tide, like bits of flotsam on a massive, invisible current. So why would a galaxy form with almost no stars? The conditions in the early universe were not uniform. In some regions, the primordial gas that collapses to form stars may have been spread too thin, or perhaps it was stirred and heated by the radiation from the first brilliant galaxies, preventing it from cooling and clumping together. The dark matter, unaffected by this radiation, would have collapsed into its halo regardless, creating a gravitational pit with almost nothing in it to light up. These dark galaxies are thought to be the cosmic equivalent of failed states, places where the recipe for a bright, starry galaxy simply never came together. They wander the voids as cosmic ghosts, detectable only by their gravitational effects on their surroundings, or, as in this case, by the debris they leave behind after a collision. How many of these phantoms might be out there, invisible to our telescopes? Their existence suggests the cosmic web is far more crowded with unseen structures than we ever realized. A hidden population of shadows that giants like Andromeda feed upon to grow their own invisible halos. The serene spiral next door did not just consume a neighbor, it absorbed a cosmic mystery. Determining the date of this galactic feast requires turning the streams themselves into cosmic clocks. Astronomers do not simply look at a stream and guess its age, they measure it with precision, using the very physics that created it. The process begins with the stream's physical appearance, its length and its width. When a galaxy is first torn apart, the stars stripped from it are relatively close together, forming a narrow, dense ribbon. Over time, however, the relentless pull of gravity acts differently on stars at the leading end of the stream versus those at the trailing end. This difference, called orbital shearing, slowly stretches the ribbon longer and longer, while also allowing it to spread out and diffuse, becoming wider and fainter. By measuring how diffuse and stretched a stream has become, scientists can estimate how long its stars have been drifting on their own. It is like watching a line of runners start a marathon together, tightly packed at the starting line. Hours later, the fastest runners are miles ahead of the slowest, and the line has stretched into a long, scattered smear of individuals across the course. The stream's condition tells us how long the race has been going. The most critical data, however, comes from the orbital dynamics of the individual stars within the stream. Using those precise velocity measurements from spectrographs, astronomers can trace each star's path backward in time through complex gravitational models. They run the cosmic film in reverse, simulating how the stream's stars would have converged. The moment when their orbits intersect, when all those scattered points come together into a single, compact object, marks the time of the merger, the instant the victim galaxy was captured and began to be dismantled. The findings from this forensic analysis are staggering. The evidence points to this particular dark matter-rich merger occurring roughly 8 to 10 billion years ago. To grasp that scale, we need to place it on a cosmic timeline. Our solar system, with the Earth forming from a swirling disk of dust and gas, is only about 4.5 billion years old. This means Andromeda was devouring this phantom galaxy for billions of years before our sun even ignited. The dinosaurs roamed, continents shifted, and humanity evolved all in a mere blink of an eye compared to the duration of this ancient, slow-motion consumption. This event did not happen in a quiet, empty universe. 8 to 10 billion years ago, the cosmos was a more violent and crowded place. Galaxies were closer together, colliding and merging with furious frequency in what astronomers call the era of galaxy assembly. Andromeda was likely a younger, smaller spiral, actively building its bulk through these dramatic encounters. The consumption of this dark galaxy was not a rare anomaly, it was a standard Tuesday in the chaotic early universe. Yet, the unique, dark matter-heavy nature of the victim left a signature so distinct that its ghostly stream persists to this day, a fossil from the universe's formative years. This timeline transforms our understanding. The serene spiral we see today is the mature, settled result of a wild and gluttonous youth. Its current majesty is built upon foundations laid by ancient acts of cosmic cannibalism, feasts so old they predate the very ground we stand on. The process begins with a fateful approach. A small, dark matter-rich dwarf galaxy drifts through the intergalactic void, its own momentum and the subtle pull of Andromeda's gravity drawing it closer. For millions of years, it seems like a harmless journey, but as it crosses an invisible boundary, the true nature of the encounter becomes clear. The side of the dwarf galaxy facing Andromeda feels a significantly stronger gravitational pull than the side facing away. This difference in force is the engine of destruction, a phenomenon called tidal disruption. It is the same force that causes our ocean tides, as the moon's gravity pulls more strongly on the side of Earth facing it. But on a galactic scale, the effect is not a gentle rise and fall of water. It is the systematic shredding of an entire star system. The victim is not swallowed whole, it is pulled apart like cosmic taffy. Imagine holding a fluffy ball of cotton by two opposite sides and slowly, steadily pulling. The center holds tight for a moment, but the outer material stretches into long, thin strands. This is what happens to the dwarf galaxy. Its outermost stars, those least bound by the galaxy's own gravity, are the first to be stolen. They are plucked away, forming two distinct tails, one flung ahead of the dwarf and one trailing behind. Over hundreds of millions of years, these tails grow longer and more diffuse, becoming the rivers of stars we now see as the stellar stream. The dark matter halo surrounding the dwarf galaxy, being more spread out and less clumpy than the stars, is even easier to strip away. It forms a broader, more massive river that flows alongside the stellar stream, creating the ghostly dark matter current detected by astronomers. What happens to the heart of the victim, its dense central core? The outcome depends on its original strength. If the core was sufficiently compact and massive, it might have resisted total dissolution. As the rest of the galaxy was stripped away, this resilient knot of stars could have survived, continuing to orbit within Andromeda's halo as a recognizable globular cluster, a lonely relic of its former self. Alternatively, if the tidal forces were overwhelming, even the core would have been stretched and smeared, its stars gradually dispersing into the general stellar halo. In the case of the dark galaxy, its core was likely that concentrated knot of dark matter, which may have remained partly intact, shepherding its few visible stars along the dark stream. The forces at play here are almost beyond comprehension, yet the timescale is what truly defies intuition. This was not a quick, violent explosion. It was a slow, inexorable unraveling that played out over billions of years. The gravitational tides that tore the galaxy apart acted with a patience that makes geology look rushed. Stars that were ripped away in the earliest stages of the merger have completed countless loops around Andromeda, their path slowly mixing and fading into the background glow. This is why the streams are so faint and diffuse. They are the fading echoes of a catastrophe that began before Earth existed. The serene spiral we see is the end result of this patient billion-year feast, a giant sitting quietly after a meal so long it has forgotten the act of eating, with only the faintest traces of debris still swirling in its gravitational grasp. The dark stream is just one chapter in a much longer, bloodier history. Andromeda's halo is not a quiet graveyard with a single monument. It is a layered archaeological site, a cosmic tell built from the ruins of many victims. The most prominent of these ruins is the giant stellar stream, a colossal river of stars so vast it wraps around a significant portion of the galaxy. This structure is the debris from a different meal entirely, one that was richer in stars and occurred more recently than the ancient dark galaxy feast. Evidence suggests this merger happened within the last few billion years, a relative blink of an eye on the cosmic clock. The scale is immense. This stream contains the remains of a dwarf galaxy perhaps 100 times more massive in stars than the one that left the dark stream. Its stars are brighter and easier to map, painting a clear, tragic arc across the sky. If the dark stream is a ghostly whisper, the giant stellar stream is a mournful song, a chorus of billions of stars singing of their lost home. But the catalogue of destruction does not end there. Scattered around Andromeda are over a dozen smaller dwarf galaxies, like the famous Messier 32 and Messier 110. These are not peaceful companions, they are the next course. Each is locked in Andromeda's gravitational grip, and telescopes reveal they are already being distorted, stretched by those same relentless tidal forces. Some show clear signs of stellar tails being pulled away, like crumbs dropping from a cookie. They are not yet fully consumed, but they are living on borrowed time, destined to become future streams in Andromeda's halo. This transforms our view of the galaxy completely. We are not looking at a predator that ate one big meal. We are looking at a serial cannibal, a cosmic giant that has grown continuously over 10 billion years by devouring whatever came too close. Its beautiful spiral disk is like the elegant facade of a great castle, while its outer halo is the untidy, ever-expanding junkyard of its conquests. Each stream, each distorted dwarf, is a stratum in this archaeological record. The deepest layer is the ancient, dark matter-rich stream from the universe's youth. Above it lies the more recent, star-rich giant stream, and at the surface are the ongoing, live disruptions of today's satellite galaxies. This is how galaxies are built, through an endless, slow-motion process of accumulation and destruction. Andromeda's serene appearance is an illusion of time and distance, masking a relentless history of galactic violence that continues to this very moment. This discovery of a pure dark matter stream is far more than just a curious footnote in Andromeda's history. It strikes at the heart of one of the greatest mysteries in modern science, the true nature of dark matter itself. Think of dark matter as the invisible skeleton of the cosmos. We see the luminous flesh of stars and galaxies, but they are only held in their majestic shapes by this vast, unseen gravitational framework. Without dark matter, galaxies would simply fly apart, their stars scattering into the void. We know it exists because of its immense gravitational pull, but we have no idea what it is actually made of. Is it a sea of exotic, undiscovered particles, or does it represent a flaw in our understanding of gravity itself? This is where the dark stream becomes a revolutionary laboratory. When two galaxies merge, their dark matter halos collide and interact. How they behave during this cosmic car crash provides a critical test for our theories. Different proposed types of dark matter would act in very different ways. Some models suggest dark matter particles are cold and slow-moving, which would cause them to clump together easily. In a merger, this cold dark matter would tend to hold on, forming dense cores that are hard to strip away. Other models propose warm or even fuzzy dark matter, made of lighter, faster particles that would be more spread out and get pulled apart more readily by tidal forces. By studying the dark stream around Andromeda, astronomers are essentially reading the forensic report from a 10-billion-year-old collision. The fact that a coherent stream of dark matter survived, flowing alongside the stars, tells us something profound about its properties. It suggests the dark matter in that victim galaxy was able to stick together, to maintain its integrity long enough to form this distinct river within Andromeda's halo. This observation acts like a filter, ruling out some theoretical models and giving weight to others. Every detail we can extract, the stream's width, its density, how closely it follows the stellar stream, is a data point in the grand experiment to identify the universe's missing ingredient. So this is not just a story about one galaxy eating another. It is a story about using the aftermath of that ancient feast to probe the fundamental architecture of reality. The dark stream is a natural experiment on a galactic scale, offering clues we could never replicate in a lab here on Earth. By deciphering this ghostly river, we are not only uncovering Andromeda's past, we are taking a small, crucial step towards solving the ultimate cosmic mystery. To reconstruct this ancient event, scientists turn to some of the most powerful tools in modern astrophysics, supercomputers running incredibly detailed simulations. These are not simple animations, they are complex mathematical universes governed by the precise laws of physics. Researchers begin by defining their suspects. They program in a model of Andromeda as it might have existed billions of years ago, and they create a digital victim galaxy with a specific size, mass, and crucially, a specific amount and type of dark matter. Then they set the encounter in motion, defining the angle and speed of the approach. With a click, the supercomputer calculates the gravitational dance between trillions of individual particles, each representing a chunk of star or dark matter over billions of years of simulated time. It is a cosmic experiment run in fast forward. The goal is singular. Can this virtual collision produce a debris field that matches the ghostly signatures we see around the real Andromeda today? Does it create a faint stellar stream that follows the exact same arc? And most importantly, does it generate a distinct, invisible river of dark matter that tugs on the stars in just the right way? The simulation is a test of our entire understanding of the event. If the simulated merger produces streams that look nothing like the real ones, the scientists know their initial assumptions are wrong. Perhaps the victim galaxy was larger or approached from a different angle, or its dark matter behaved in an unexpected way. So they adjust the parameters and run the simulation again and again and again. This process of trial and error is a form of cosmic forensics. Think of it like reconstructing a car crash for investigators. They take the final positions of the vehicles, the skid marks on the road, and the debris scattered across the pavement. Then, using physics models, they work backward, testing different speeds, angles, and braking patterns in a simulation until they find the one scenario that perfectly reproduces the wreckage at the scene. The dark stream and stellar streams around Andromeda are the skid marks and debris on a galactic highway. The supercomputer simulations are the accident reconstruction software, helping us determine the exact conditions of the crash that happened 8 billion years ago. Through this painstaking digital archaeology, scientists have been able to narrow down the properties of the victim galaxy with remarkable precision. The simulations that work best tell us it was indeed a dark matter-dominated phantom, relatively small in starlight but immense in gravitational presence, and that it was pulled apart on a very specific plunging orbit. These virtual recreations do more than just confirm a story. They allow us to witness the cataclysm itself, to watch in a matter of hours a process that took longer than the age of our planet. We see the first gravitational tug, the stretching into tidal tails, and the slow, graceful winding of those tails into the vast streams that still linger today. It is through these digital windows that a theoretical idea becomes a visible, testable history, proving that the serene spiral next door was once the scene of a devastating and beautiful act of cosmic destruction. Andromeda's dark stream is not a unique tragedy, but a single verse in a universal epic of creation and destruction. This process of galactic cannibalism is the fundamental engine of growth across the cosmos, a rule of nature as true in the farthest reaches of space as it is in our own galactic backyard. To understand its scale, we must pull our gaze back from Andromeda and look at the wider universe where astronomers have captured countless galaxies in the very act of merging. These cosmic collisions are not rare or hidden. They are splashed across the sky for anyone with a powerful enough telescope to see. Consider the Mice galaxies, a pair of spirals located 300 million light-years away, caught in a breathtaking gravitational dance. In telescope images, you can clearly see two distinct galactic cores, but from each one streams a long, luminous tail of stars and gas stretched out by their mutual tidal forces. They look like two mice scurrying through the void, connected by their celestial tails, offering us a snapshot of the early stages of a merger that will one day result in a single, larger galaxy. An even more dramatic example lies in the antennae galaxies. Here, the collision is more advanced. The two spiral galaxies have already passed through each other, and the violent interaction has triggered a firestorm of new star birth. The classic spiral shapes are utterly destroyed, replaced by a chaotic, glowing core and two enormous, streaming arcs of material that resemble the antennae of an insect. This is a stellar nursery of unimaginable scale, fueled by the shock waves and compressed gas of the collision. These systems show us the process in real time, the beautiful, violent chaos that precedes the formation of a new, settled galactic giant. They are living proof that the serene galaxies we often admire are merely the calm after a long and stormy history of mergers. This grand narrative hits closer to home than you might think. Our own Milky Way is not an innocent bystander in this cosmic food chain. It is a predator with its own bloody history. Recent data from the Gaia Space Observatory has peeled back the layers of our galaxy's past, revealing the ghostly remains of ancient meals within our own stellar halo. The most significant of these is the Gaia Enceladus galaxy, sometimes called the Gaia Sausage. This was a dwarf galaxy roughly 1/4 the mass of the Milky Way that collided with and was consumed by our galaxy around 10 billion years ago. The evidence is written in the motions of millions of stars, which move on distinct radial orbits like a swarm of bees, a clear signature of a long assimilated victim. This colossal merger fundamentally shaped the Milky Way, likely contributing to the thick disk of stars we see today and enriching our galaxy with a wave of new material. We are quite literally living in the digested remains of a conquered neighbor. This universal process is known as hierarchical galaxy formation, the grand theory that explains the structure of our universe. It posits that the largest galaxies we see today were not born giant, but were assembled over billions of years through the relentless merging of smaller building blocks. The early universe was filled with countless small proto-galaxies, swirling in the dark matter scaffolding of the cosmic web. Gravity drew them together, they collided, merged, and grew. These mergers triggered bursts of star formation, built up central black holes, and sculpted the majestic shapes of spirals and ellipticals. Andromeda's dark stream, the antennae's fiery chaos, and the ghost of Gaia Enceladus within us are all chapters in the same story. Every giant galaxy is a cannibal, its current form a testament to every smaller galaxy it has ever consumed. This shifts our perspective entirely. The beautiful islands of light we see in the night sky are not isolated kingdoms, but the bustling, ever-evolving metropolises of a connected cosmic empire, all built upon foundations of ancient conquest. This relentless history of cosmic feasting is not a closed book, but a prelude to the greatest meal of all. Our own galaxy, the Milky Way, is on the menu. In about 4.5 billion years, the serene spiral we see today and the beautiful spiral of Andromeda will cease to exist as we know them. Their long, slow gravitational dance will culminate in a direct collision, the ultimate act of galactic cannibalism where neither participant survives intact. Instead, they will merge into a single, colossal new galaxy that astronomers have playfully nicknamed Andromeda. This is not speculation, it is an inevitable future written in the stars. Precise measurements from telescopes like Hubble have tracked Andromeda's motion. It is currently hurtling toward us at an astonishing 250,000 miles per hour. But do not picture a head-on crash. The distances are so vast that the encounter will be more of a slow-motion gravitational tango that lasts for billions of years. The first close pass will happen in roughly 4 billion years. From a hypothetical future Earth, the night sky would transform utterly. As Andromeda approaches, it would swell from a faint smudge into a breathtaking, filling a larger and larger portion of the heavens. The two spiral disks, each containing hundreds of billions of stars, will begin to interact. But here is the astonishing thing. Space is so empty that actual stellar collisions will be incredibly rare. The stars are like tiny specks of dust separated by miles of void. They will mostly just glide past one another. The real violence will be gravitational. The immense tidal forces will warp and distort both galaxies beyond recognition. Their elegant spiral arms will be pulled into long, streaming tails of stars and gas, much like the antennae galaxies we see today. These majestic arcs will intertwine, weaving a temporary celestial tapestry of unimaginable scale and beauty. Over the next 1 to 2 billion years after that first pass, the two galaxies will swing apart, then fall back together in a series of ever-closing loops. With each passage, they lose orbital energy, drawn closer by their mutual gravity until they finally coalesce. The final merger will be a fiery, chaotic blaze of new star formation as colliding gas clouds compress and ignite. The resulting object, after perhaps another billion years of settling, will not be a spiral. The violent, randomized orbits of the stars will create a vast, featureless, football-shaped giant known as an elliptical galaxy. This is Andromeda, a titan born from the complete consumption of two proud spirals. The stellar archaeology of this new galaxy will be a historian's dream and nightmare. The ghostly streams from Andromeda's past meals, like the Dark Stream and the Giant Stream, will not vanish. They will be joined by new, colossal streams formed from the tidal shredding of both galaxies during their merger. And they will mix with the ancient streams already hiding in the Milky Way's halo, like the remains of the Gaia Enceladus galaxy. The halo of Andromeda will be an impossibly complex web of stellar rivers, a tangled record of two separate histories of cannibalism finally braided together. Deciphering which stars came from which victim and when would be a puzzle spanning the lifetime of a galaxy. From the perspective of any future civilization gazing up, the serene, structured night sky we know will be gone, replaced by the dazzling, chaotic glow of a galactic core and a heaven strewn with the luminous scars of a colossal creation. The quiet spiral we call home is living on borrowed time, destined to become both a devourer and the devoured in the universe's endless feast. Yet for all we have uncovered, the dark stream remains a profound enigma. It raises as many questions as it answers, reminding us that every discovery in science is a doorway to deeper mysteries. The most fundamental question is the identity of the victim itself. Was it truly a pure dark galaxy, a phantom of the cosmos with almost no stars? Or was it simply a normal dwarf galaxy with an unusually resilient and massive dark matter halo? The distinction is crucial. A true dark galaxy would represent a failed state of cosmic evolution, a place where the universe's recipe for starlight simply never worked. But if it was a normal dwarf, it forces us to question why its dark matter was so tightly bound, so resistant to being mixed into Andromeda's halo. Our current data points toward the former, a ghost ship of dark matter, but astronomers need more evidence, more streams to be certain. This leads directly to the next haunting question: how many more of these invisible rivers are flowing through the cosmos? If one exists around our nearest galactic neighbor, it is statistically almost certain that others are out there, circling distant giants. Our ability to detect them, however, is incredibly limited. Finding a dark stream requires first finding a visible stellar stream to act as a tracer, and then having the sensitivity to measure the subtle gravitational anomaly within it. We are essentially searching for ghosts by watching how they disturb a faint mist. There could be dozens, even hundreds, of similar dark matter streams woven through the halos of galaxies across the universe, a hidden network of ancient conquests we are only beginning to sense. Finally, and most importantly, what does this specific stream tell us about the dark matter particle itself? The very fact that it formed a coherent, lasting structure challenges some of the more exotic theoretical models. For instance, if dark matter were warm or fuzzy, made of extremely light particles, it would be more spread out and less prone to clumping. Such dark matter might not have survived the tidal disruption in such a distinct stream. It would have dissipated and mixed much more quickly. The persistence of Andromeda's dark stream after 8 billion years suggests the dark matter involved is cold, slow-moving, and good at holding together in dense clumps. Yet, even this conclusion is provisional. The stream's precise width, density, and how it shepherds the visible stars are all details that future telescopes will measure with far greater precision. Each new measurement will act as a filter, straining out theories that do not fit and bringing us closer to the true identity of the universe's dominant substance. So the story does not end with a solved case, but with an open investigation. The dark stream is both evidence and question, a relic that confirms the violent process of galactic cannibalism while simultaneously challenging us to define the very fabric of reality. It is a beautiful reminder that the universe is not a puzzle to be completed, but a mystery to be endlessly explored, with each answer revealing a new, more fascinating layer of questions waiting in the dark. The hunt for these cosmic ghosts has only just begun. Astronomers are now scanning the skies with a new generation of tools designed to see the faintest whispers of light in the universe. Their primary target is our own galactic neighbor, Andromeda, but their ambition stretches to the edge of the observable cosmos. The goal is to map the full archaeological record of its growth, to find every single stellar stream and, hidden within them, the signature of every dark stream. This is not a simple task. These structures are incredibly faint, often lost in the glare of the galaxy's bright core or drowned out by the foreground stars of our own Milky Way. It requires patience, immense computing power, and instruments of almost unimaginable sensitivity. Current telescopes like Subaru and the Canada-France-Hawaii telescope have given us our first glimpses, revealing the giant stream and hints of others. But they are like using a flashlight to explore a vast, dark cave. We see only what is directly in the beam. To illuminate the entire cavern, we need a new kind of light. That light is coming from two revolutionary observatories now being built. The Vera C. Rubin Observatory, perched on a mountaintop in Chile, will begin its legacy survey of space and time in a few years. Its mission is nothing less than a decade-long cinematic record of the entire southern sky. Night after night, its enormous mirror and giant camera will capture deep, wide-field images, detecting objects billions of times fainter than the human eye can see. For stream hunters, this is a game-changer. The Rubin Observatory will not just look at Andromeda, it will watch it over and over. This repeated viewing allows astronomers to stack images, enhancing the faint glow of streams that would be invisible in a single snapshot. More importantly, it will measure the precise motions of millions of individual stars within Andromeda's halo. By tracking which stars are moving together, it can identify streams statistically, even before their faint light is clearly seen in an image. It is like identifying a school of fish in murky water, not by seeing the fish, but by detecting the synchronized pattern of their movement. Following closely will be the Nancy Grace Roman Space Telescope, a NASA observatory set to launch around the middle of this decade. While Rubin scans from the ground, Roman will operate from the pristine darkness of space, free from the blurring effects of Earth's atmosphere. Its infrared vision is perfectly suited to peer through the dusty plains of galaxies and see the older, redder stars that make up most tidal streams. Roman's wide-field infrared camera will provide a crystal-clear, deep census of stellar populations around thousands of galaxies. Together, these telescopes will transform a delicate art into a robust science. They are expected to reveal not just one or two more streams around Andromeda, but potentially dozens, a complete fossil record of its cannibalistic history. Each newly discovered stream will be another chapter in the biography of the giant next door, but the ambition extends far beyond our local group. These observatories will perform the same forensic analysis on millions of distant galaxies. For the first time, we will have a large enough sample to understand galactic cannibalism as a universal process. We will see how the size, number, and type of streams differ between spiral and elliptical galaxies, between giants in crowded clusters and isolated field galaxies. This statistical power will answer fundamental questions. Do all galaxies grow the same way? Is the dark stream around Andromeda a rare event or a common signature of consuming dark matter-rich victims? We are on the cusp of moving from studying individual crime scenes to understanding the patterns of cosmic crime across the entire universe. The faint rivers of stars we seek are more than just debris. They are the written history of the cosmos, and we are finally building the telescopes that can read it. The dark stream is not merely a fossil, it is a blueprint. This single, ancient act of cannibalism offers a precise template for the fundamental process that built the universe as we see it, a model astronomers call hierarchical merging. Imagine the cosmos not as a collection of finished sculptures, but as an endless construction site. In the early universe, gravity drew together the first small clumps of dark matter and gas. These were the cosmic bricks, the primordial dwarf galaxies. Over billions of years, these bricks collided and stuck together, assembling larger and larger structures through mergers and acquisitions. A small group of dwarfs merges into a modest spiral. That spiral then consumes a few more dwarfs, growing larger. Eventually, two sizable spirals might collide to form a giant elliptical galaxy. This is hierarchical merging, the universe's slow, patient method of building its grandest architecture. Every galaxy we see, from the smallest dwarf to the largest elliptical, is a product of this relentless bottom-up assembly. Andromeda's dark stream is a pristine example of one of the earliest steps in this process, the consumption of a fundamental building block. By studying it, we are not just reading a single chapter of Andromeda's history, we are observing the foundational paragraph in the story of how any giant galaxy comes to be. This model explains the stunning diversity of galactic forms in the night sky. Why does one galaxy have a delicate, thin disk of stars like a spinning plate, while another is a fuzzy, football-shaped elliptical blob with no discernible structure? The answer often lies in its diet, in the specific types of mergers it experienced. A galaxy that grows primarily by quietly absorbing small, dark matter-rich dwarfs, like the one that left the dark stream, can maintain its orderly spiral disk. The accretion is gentle and diffuse, not disruptive enough to destroy the delicate rotational motion of its stars. This process, however, steadily puffs up the galaxy's outer halo, adding a vast, faint sphere of ancient stars. Andromeda's thick halo is a direct result of billions of years of this kind of snacking. In contrast, a major merger between two galaxies of similar size is a catastrophic event. It violently randomizes the orderly orbits of stars, destroying any thin disk and leaving behind a chaotic, puffed-up elliptical galaxy. The beautiful spiral shapes we cherish are therefore not permanent. They are temporary, delicate states of balance, maintained only as long as the galaxy avoids a devastating collision with an equal partner. The dark stream discovery helps calibrate this entire model. It gives astronomers a specific, measurable example of the quiet feeding mode. By knowing the exact properties of the victim and the timing of the merger, they can refine their simulations of how dark matter and stars behave during these events. This, in turn, helps them predict how such an accretion event would influence the larger galaxy's growth, its chemical composition, and even the future formation of stars within it. Ultimately, every stream of stars we find is a data point in a vast cosmic equation. By collecting enough of these points from Andromeda and from galaxies across the universe, we move from a general theory to a precise history. We begin to understand not just that galaxies grow by merging, but exactly how different merger recipes produce the breathtaking variety of galactic forms we see when we point our telescopes at the deep sky. The serene spiral next door, with its hidden river of dark matter, is a living lesson in cosmic construction, showing us how the largest structures in existence are built one invisible brick at a time. This cosmic history is not a distant spectacle, it is our family story. Every atom in your body, from the calcium in your bones to the iron in your blood, carries the legacy of these ancient galactic feasts. The elements essential for life were not created in the calm heart of a single, solitary star. They were forged in the furnaces of countless stars across generations, many of which lived and died in galaxies that no longer exist as independent entities. When Andromeda consumed that dark galaxy, or when the Milky Way devoured Gaia Enceladus, they were not just mixing stars, they were mixing the raw materials for future planets and life. The carbon, nitrogen, and oxygen that make up your very being are interstellar travelers, refugees from stellar explosions that occurred billions of years ago in different corners of space, later swept up in these grand mergers. We are, in the most literal sense, made from the digested remains of conquered worlds. Understanding galactic cannibalism, then, is a form of cosmic genealogy. It helps us trace our elemental ancestry back through not just stellar life cycles, but through the very architectural history of our galaxy. We are not merely inhabitants of the Milky Way, we are products of its violent and acquisitive past. The serene night sky we look upon is not a static painting. It is a single frame in a billion-year movie of construction and destruction, and we are here because of every collision, every merger that came before. This perspective fundamentally changes our sense of place. For centuries, we viewed galaxies as immutable islands, lonely and isolated in the void. We now know they are dynamic, social creatures, constantly interacting, merging, and reshaping one another. The Milky Way is not a fortress, it is a bustling crossroads, its form and composition directly shaped by every encounter it has ever had. Our solar system orbits a star that may well have been born in a different, smaller galaxy that was consumed long ago, its original home now completely dissolved into the halo. This makes our place in the universe not smaller, but profoundly more connected. We are participants in an epic of change so vast it defies comprehension, yet it is written into the chemistry of our cells. To care about a dark stream around Andromeda is to care about the chain of events that led to our existence. It answers the deepest human question of where we came from, not just biologically, but atomically and galactically. It tells us that stability is an illusion on cosmic timescales, that change is the only constant, and that our home is not a fixed point but a temporary arrangement in an endless dance. This knowledge is a humbling and empowering gift. It places us within the flowing narrative of the cosmos, reminding us that we are not just observers of the universe, but are, in every particle, an expression of its turbulent and creative history. But how do we visualize a river of invisible matter flowing through space? The answer lies in a remarkable collaboration, a fusion of science and art that turns data into understanding. Astronomers provide the raw numbers, the velocities of stars, the gravitational maps, the supercomputer simulations. Artists and scientific visualizers then take this information and translate it into images and animations we can see and feel. They are the interpreters of the invisible, building bridges between complex equations and human imagination. These visualizations are not mere artistic guesswork, they are grounded in rigorous physics. Every stream of light, every distortion of a galaxy's shape, is based on a real data point or a validated simulation. The artist's role is to choose the viewpoint, the color palette, and the lighting to tell the story most clearly. For the dark stream around Andromeda, a visualizer might start with the precise orbital path calculated by astronomers. They would render the faint, wispy trail of visible stars in cool blues or whites. Then, to represent the dark matter, they might use a contrasting, semi-transparent ripple of deep red or purple, flowing in tandem with the stars but broader and more diffuse. This color choice is not arbitrary, it visually distinguishes the two components, making the abstract concept of a dual stream instantly graspable. We have all seen these breathtaking results, perhaps without realizing their scientific fidelity. The iconic Hubble Space Telescope images of colliding galaxies, like the antennae, are often enhanced and colorized to highlight different elements. Hydrogen gas in red, older stars in blue, dust lanes in brown. These choices are guided by the specific wavelengths of light detected by the telescope's instruments. Similarly, fly-through animations of galaxy mergers, which show two spirals gracefully intertwining and erupting into fireworks of new stars, are direct outputs from supercomputer models. The computer calculates the position of every simulated star particle at each time step, and the visualizer simply renders that exact data as a luminous point of light. This partnership is crucial for public comprehension. Dark matter is, by definition, impossible to photograph. Without these data-driven visualizations, the concept would remain a dry entry in a physics textbook. Art makes the intangible tangible. It allows us to witness the slow dance of tidal disruption, to see the ghostly rivers of stars being pulled from a dwarf galaxy, and to comprehend the vast, invisible scaffold of dark matter that guides it all. These images do more than educate, they inspire. They evoke the awe and wonder that drives scientific curiosity in the first place. A child who sees a vivid animation of galaxies colliding is not just learning astrophysics, they are feeling the scale and drama of the cosmos. That emotional connection is a powerful catalyst for the next generation of scientists, artists, and explorers. In this way, the dark stream is more than a scientific discovery, it is a muse. It challenges both the astrophysicist to model its physics and the artist to give its ghostly form a visual voice. Together, they transform columns of numbers into a shared story, allowing all of us to stand at the edge of an invisible river and finally see its current flowing through the dark. Yet the scientific process demands we question even our most compelling stories. Could the dark stream be explained by something other than the consumption of a phantom galaxy? Astronomers have proposed several alternative hypotheses, each rigorously tested against the growing body of evidence. One intriguing possibility is that this structure is not a remnant of a separate galaxy at all, but a vast tidal feature born from a far more complex multi-galaxy interaction. Picture not a single victim falling into Andromeda's grasp, but a chaotic ballet involving several of its satellite dwarfs. Their mutual gravitational tugs and pulls, combined with Andromeda's dominant influence, could have stirred the galactic halo into a complex pattern of ripples and streams. In this scenario, the dark matter anomaly might be a gravitational echo of that group dance, a dense knot in the fabric of the halo created by the overlapping tides of several smaller mergers. It would be a signature of a messy dinner party, not a solitary feast. Another line of inquiry questions whether the stream is even external. Could it be a colossal warp or ripple within Andromeda's own extended disk, a structure flung out from the main galaxy during a violent event in its past? Our own Milky Way's disk is not perfectly flat. It shows a subtle warp, likely caused by a past encounter. Perhaps Andromeda experienced a more dramatic version, leaving a persistent, coherent structure that we now misinterpret as an accretion stream. These alternatives are not dismissed lightly. They are essential counterpoints that strengthen the investigation. Science advances not by accepting the first appealing answer, but by relentlessly pitting every plausible idea against the cold, hard data. So how do researchers test these competing visions? They return to the supercomputer simulations, but now they input different initial conditions. They model the gravitational dance of multiple dwarf galaxies. They simulate a massive impact that could warp Andromeda's disk. They run these virtual experiments thousands of times, searching for any combination that reproduces the exact observed properties of the stream, its shape, stellar velocities, and that critical dark matter signature. To date, the model of a single, dark matter-rich merger remains the most parsimonious fit, the simplest explanation that accounts for all the clues, but the debate is far from closed. Each new observation, each sharper image from upcoming telescopes, acts as a judge. Does the stream's chemical composition match stars known to form in isolated dwarf galaxies, or does it match Andromeda's own outer disk? Do we find other, fainter streams that clearly connect to this one, suggesting a more complex debris field? This healthy skepticism is the engine of discovery. It ensures that our cosmic story remains faithful to the evidence, always ready to be rewritten by a new and better piece of the puzzle. This billion-year-old crime scene has been pieced together with a detective's patience and a physicist's precision. Astronomers did not simply stumble upon the dark stream. They built a case for it, clue by painstaking clue, using methods that would feel familiar to any investigator. The first pieces of evidence were the faint, ghostly trails of stars themselves, the visible wounds in Andromeda's halo, but like a detective finding a single fingerprint that was only the starting point. The real breakthrough came from interrogating those stars, measuring their precise motions to understand not just where they are, but where they have been. Each star's velocity is a sworn statement, a testimony to the gravitational forces that have acted upon it for eons. By compiling millions of these testimonies, scientists could map the invisible hand of gravity shaping the stream, revealing the presence of the dark matter river flowing silently beside it. This is forensic astronomy, where the crime scene is light years across, and the evidence has been cooling for longer than our planet has existed. The tools are telescopes and spectrographs, but the process is one of meticulous deduction, connecting subtle anomalies to a narrative of ancient violence. To make sense of it all, they turn to the cosmic equivalent of crime scene reconstruction, the supercomputer simulation. These digital models allowed them to test countless scenarios, rewinding the tape of the universe to find the one sequence of events that perfectly recreated the stellar streams and gravitational tugs we see today. It was a process of elimination, ruling out mergers that were too violent, too gentle, or from the wrong angle, until only the story of the dark galaxy remained. This synthesis of observation and simulation is the beating heart of modern astrophysics. It demonstrates a profound truth about studying the cosmos. We cannot run experiments in the traditional sense. We cannot smash galaxies together in a lab. Instead, we must be brilliant observers and even more brilliant interpreters, using the universe itself as our laboratory and its ancient light as our data. The dark stream case is a masterclass in this approach, showing how human ingenuity can bridge the gap between the directly observable and the profoundly hidden. It required accepting timescales that dwarf human history and grappling with a substance that refuses to be seen. Every conclusion about this event, from the victim's composition to the date of the merger, is an inference built upon a mountain of indirect evidence, a testament to the scientific method operating at the very limits of perception. The serene spiral of Andromeda, therefore, is more than a beautiful island of stars. It is a cosmic cold case file, now solved, reminding us that the universe is always whispering its secrets to those who know how to listen. Andromeda will not reign forever. This colossal elliptical galaxy, born from the merger of two spirals, will face a future dictated by the universe itself, a fate of fading light and profound isolation. For trillions of years, it will continue its cannibalistic ways, consuming any remaining dwarf galaxies within its gravitational reach, growing ever more massive and diffuse. Its central black holes will have long since merged into a single, quiescent monster, and the furious burst of star formation triggered by the collision will have burned out. The galaxy will enter a long, slow autumn. Its supply of interstellar gas, the raw material for new stars, will be exhausted, either turned into stars or blown away by stellar winds and supernova. One by one, the brilliant, short-lived blue giant stars will flicker out. The galaxy's color will steadily redden as only the longer-lived, cooler stars remain. Eventually, even these red dwarfs, which can shine for trillions of years, will begin to die. The galaxy will dim, its light softening into a pale, ruddy glow. This is the stellar era's end, a time when the lights of the universe begin to switch off. New stars will no longer be born, and the old ones will slowly wink out. Andromeda will become a galaxy of stellar remnants, a graveyard filled with the fading embers of white dwarfs, the dense cinders of neutron stars, and the silent black holes left behind. It will be a monument to a more vibrant, violent past, a fossil of a bygone cosmic age. This lonely fate is sealed by the universe's accelerating expansion. The space between galaxy clusters is stretching at an ever-increasing rate, driven by the mysterious force we call dark energy, while Andromeda will remain gravitationally bound with its immediate neighbors in what was once the local group. The vast world beyond will recede. Over hundreds of billions of years, every other galaxy cluster will be pulled away by the stretching fabric of space, their light red shifted into invisibility. From the perspective of any civilization within Andromeda, the observable universe will have shrunk dramatically. The night sky, once filled with the faint smudges of distant island universes, will go utterly, permanently black. No new light from beyond the local cluster will ever arrive. Andromeda and its few surviving satellite galaxies will become a lonely island in an infinite dark sea, the only visible matter in an otherwise empty cosmos. This isolation is absolute, a prison built not by walls, but by the fundamental geometry of reality itself. The great story of galactic cannibalism, of growth through merger, will be over because there will be nothing left to merge with. The timeline for this is almost inconceivably vast. We measure it not in billions, but in trillions of years. On this scale, the entire 10-billion-year history of galactic cannibalism that built Andromeda and the Milky Way is merely the opening act. The universe will enter the degenerate era dominated by those cooling stellar remnants. Planets will have frozen, their orbits decayed, complex chemistry, and certainly life as we know it will be impossible. Eventually, over timescales so long they make atoms seem eternal, even these remnants may evaporate through theoretical processes like proton decay, leaving behind only black holes. And in the almost poetic final chapter, those black holes themselves will slowly evaporate away via Hawking radiation, releasing their mass back into the universe as a faint whisper of particles. What began with a brilliant flash of light and a feast of galaxies will end in darkness, silence, and heat death. This ultimate context transforms our story. The dark stream around Andromeda is not just evidence of a single ancient meal. It is a fleeting signature from the universe's vibrant, constructive youth. It captures a moment when galaxies were building, colliding, and growing, when the cosmic food chain was active and rich. That era, for all its violence, was one of brilliant light and dynamic change. To study this stream is to recover a memory from that lost time, a clue to how the universe built its greatest structures before the long, slow fade into darkness began. The story of galactic cannibalism is not locked away in research papers. It is written across the night sky for anyone to read. You can witness the evidence of this ancient drama with your own eyes by finding the Andromeda galaxy itself. On a clear, moonless night far from city lights, look toward the constellation of Andromeda in the autumn and winter months. From the northern hemisphere, this is when it is highest in the sky, offering the best view. You can locate it by finding the Great Square of Pegasus, a distinctive pattern of 4 bright stars. From the top left star of the square, trace a line of 2 fainter stars leading away. Just beyond that second star, you will see a faint, elongated smudge of light. That is it. To the naked eye, it is a mysterious, fuzzy patch. Through a pair of ordinary binoculars or a small backyard telescope, that smudge resolves into a soft, glowing oval of light with a brighter core. You are not looking at a cloud. You are gazing directly at the combined light of roughly 1 trillion stars, a city of suns so distant its light has been traveling for 2.5 million years to reach your retina. Within that soft glow, you are seeing the integrated light of Andromeda's entire history, including stars from its original disk and, invisibly mixed among them, the ancient, digested stars from its many victims, like the phantom dark galaxy. Your telescope cannot separate them, but their combined starlight is the proof. You are seeing the predator and its meals all at once. This simple act of observation connects you directly to the cosmic story, making you a witness to the grand, slow-motion processes that shape our universe. But you can become more than a witness. You can become an active participant in this discovery. Astronomers need help sifting through the mountains of data from telescopes, and that is where you come in. Online citizen science platforms like Zooniverse host projects where anyone can help. You might be asked to classify images of distant galaxies, identifying those that are merging or show signs of tidal disruption. Your human pattern recognition can spot odd shapes and faint streams that computer algorithms sometimes miss. Another project might invite you to scan detailed maps of the Milky Way's halo, searching for the subtle overdensities that signal a stellar stream from one of our own galaxy's ancient meals. By contributing just a few minutes of your time, you become part of a global team of cosmic archaeologists, helping to uncover the next chapter in the story of galactic cannibalism. The universe's history is not a closed book, it is an ongoing excavation, and with a pair of binoculars and an internet connection, you hold a trowel in your hand. So the serene spiral hanging in our night sky is, and has always been, a hungry giant. Its beauty is a mask for a history of cosmic cannibalism, a patient feast stretching back to the dawn of time. We began by admiring a tranquil island of stars, only to peel back the layers and find a predator, its halo littered with the ghostly remains of past meals. The discovery of the dark stream was the ultimate clue, a river of pure dark matter flowing silently from a victim consumed before our planet even existed. This single, ancient thread connects the grandest themes of modern astronomy. It reveals the violent process of hierarchical merging that builds every giant galaxy. It serves as a natural laboratory to probe the mysterious nature of dark matter itself, and it rewrites the biography of our nearest galactic neighbor from a quiet neighbor to a serial cannibal. This story transforms our universe from a static gallery of beautiful objects into a dynamic, living arena. It is a place of breathtaking violence and equally breathtaking creation, where the largest structures we can see are shaped by ancient acts of destruction. Every majestic spiral, every glowing elliptical, is a testament to a long history of collisions, mergers, and slow-motion feasts. We are living in the digested remains of such events, our very atoms forged in stars that belong to galaxies that no longer exist. Our curiosity has led us to map these invisible rivers and decipher these gravitational ghosts, reminding us that our place is not as distant observers, but as tiny, conscious participants in an epic that spans billions of years. We look up at Andromeda not just to see a smudge of light, but to read a chapter in the autobiography of the cosmos, written in streams of stars and rivers of shadow. This cosmic story is now yours to continue. In the comments below, I would love to hear which part of this journey resonated with you the most. Was it the ghostly dark stream itself, the forensic science used to find it, or the staggering idea that our own galaxy has a similar violent history? What do you imagine the ultimate fate of Andromeda will be 1 trillion years from now? Share your thoughts and questions, and if you enjoyed this deep dive into the universe's hidden narratives, be sure to subscribe. We explore mysteries like this every week, peeling back the serene surface of the cosmos to reveal the astonishing stories written in starlight and shadow. The next time you look up at the Andromeda galaxy, remember, you're not just looking at a neighbor, you're looking at a predator, and its dinner bell might still be ringing.